As sir told, myself, Dr. Uma Mahesh RN, I am working as a faculty in Mysore in ATME College of Engineering, Karnataka. So my talk is about the topic called Deep Convolutional Neural Network for Three-Dimensional Application using Face-Only Digital Holographic Information. I'll tell how to construct the 3D object and how the hologram is recorded and how the face information is reconstructed. Then I will talk about the deep learning architecture, results and discussions, and then conclusion and references. So first of all, what is digital holography? So when I consider a three-dimensional object, I'll be having both amplitude and phase information. When I capture the image of a three-dimensional object, I'll be getting only the amplitude information. The phase information will be lost. So in order to obtain both phase information as well as intensity information, we will go for digital holography technique. So what we will do in digital holography is on the three-dimensional object information, we will superimpose a plane reference wave and we will combine both object wave and reference wave in order to obtain a fringe pattern which contains both amplitude and phase information. So O is the amplitude of the object wave, phi is the phase of the object wave, R is the amplitude of the reference wave, delta is the phase angle of the reference wave. So in this manner, in holography, we can obtain both amplitude as well as phase information. This amplitude and phase information will be recorded in the form of interference fringe pattern, which will be recorded by the digital devices like CCD and CMOS sensors. That's why it is called as digital holography. So next thing is in digital holography, we will be using object wave as well as reference wave. We will combine both object wave as well as reference wave in order to generate the fringe pattern. That interference fringe pattern is called as hologram. So after recording the hologram, we will be using numerical reconstruction algorithm in order to obtain phase and amplitude information of the object wave. So here I have represented the holographic principle. We will be using coherent light source, that is a laser light source with a constant wavelength and constant phase difference of 0 degree. This laser light beam will be passed through the beam splitter, where some part of the light beam will be passed through the object and remaining part of the light beam will be passed through the another portion of the setup. So this is the experimental setup. Here the laser light source will be passed through the beam splitter. The object wave will be created through the object. The laser light beam will be passed through the object and it will create an object wave. And the remaining light beam will be passed through another mirror and it will create a reference wave. Both object wave and reference wave gets interfered in order to form interference fringe pattern. That interference fringe pattern is called as hologram. That hologram will be recorded by either digital devices, CCD and CMOS sensors, or either photographic plates. So here we will be using digital device in order to form the hologram. So O of x comma y represents the equation for the object wave. R of x comma y represents the equation for the reference wave. I of x comma y represents the intensity of the recorded hologram, which contains reference wave, object wave, and twin wave, twin image wave. Twin image wave means it contains real image as well as virtual image. So the first term represents the amplitude of the reference wave. Second term represents the amplitude of the object wave. Third term represents only the object wave. Fourth term represents the conjugate of the object wave. So this is how we will form the hologram. This hologram will be formed and then it will be passed through the numerical reconstruction process, numerical reconstruction algorithm in order to generate the phase information. Next, we will be using deep learning in order to perform classification and other kinds of applications in deep learning. So next, I will be using three-dimensional object in order to form the data set. I have considered 4 three-dimensional objects in this particular experiment: triangle, square. I'll be using square in the front plane and a triangle in the back plane. The front plane and back plane is separated by a depth called d. So first, I will capture the information from the front plane. Then I will capture the information from the back plane. I will combine both front plane as well as back plane information at the charge coupled device in order to form object wave. Then I will be using reference wave, where the reference wave will be having at different phase angles. At 0 degree, I will be using one reference wave. At 90 degree, I will be using another reference wave. So at different phase angles, I will be using different plane reference waves, and I will be combining with object waves in order to form the fringe pattern. After recording the fringe pattern, I will be reconstructing it in order to obtain the phase information. I have constructed 4 three-dimensional objects like this. Triangle, square, I have considered in one set. Circle, square, circle I have considered in the front plane, square in the second plane, square in the first plane, triangle in the second plane, triangle in the first plane, circle in the second plane. Then I have formed the data set for 2880 images, where I have considered 75% for training, 15% for validation, 10% for testing. Training images and validation images. So here you can see the reconstructed phase image of one of the 3D objects, that is circle square, that I have obtained using phase shifting digital holography technique. Next, I have used convolutional neural network architecture in order to perform the binary classification. So after reconstructing the phase image from the hologram, the reconstructed phase image will be of size 512 into 512. This 512 into 512 image will be passed through the first convolutional layer, where I have considered 8 kernels in the first convolutional layer, 16 kernels in the second convolutional layer, 32 kernels in the third convolutional layer, 64 kernels in the fourth convolutional layer. So this convolutional neural network contains 4 stages of convolutional layers and 4 stages of pooling layers. The output of the final pooling layer will be given to the classification layer to produce the final output. So this is the working of the convolutional neural network. Next, I have performed two-dimensional convolution operation in the convolutional layer. If I consider 6x6 input and a 3x3 kernel, the 3x3 input will be multiplied with 3x3 kernel to obtain a single pixel in the output feature map. This convolutional output will be passed through the nonlinear activation function in the convolutional layer, where I have used rectified linear unit activation function. This rectified linear unit activation function will consider the values for the right side of the x-axis and discard the values for the left side of the x-axis. So after performing convolution operation in the convolutional layer, that convolutional layer output will be passed through the pooling layer. So pooling is also one of the dimensionality reduction techniques. I have performed max pooling technique in the convolutional neural network. So if I consider 4x4 input, max pooling 2D means in the two-dimensional matrix, it will consider the maximum pixel among the existing pixels. So for example, in 2x2 matrix 1, 2, 2, 3, 3 will be considered because it is the maximum pixel. 3, 4, 4, 5, 5 will be considered. 3, 4, 4, 5, 5 will be considered. 5, 6, 6, 7, 7 will be considered. So this is the model summary of the CNN, which is I have used for the binary classification. 512 into 512 into 8, I have used 8 kernels in the first convolutional layer, 16 kernels in the second convolutional layer. I have taken 5x5 kernel size, 32 kernels in the third convolutional layer, 64 kernels in the fourth convolutional layer, and I have performed dimensionality reduction for 4 stages. 4 times I have done convolution, 4 times I have done pooling. 50% of the feature map will be reduced. So how I will get the output? If you see the convolution operation, 6x6 input is reduced to 4x4. So similarly, 512 into 512 is reduced to 508 into 508 because I have taken kernel sizes 5x5. So n minus k plus 1. N is 512, k is 5, and plus 1 is bias. Similarly, this 508 will be reduced to 254. 254 will be reduced to 250 because I have used 5x5 kernel and 50% of the dimensionality reduction will take place. So like this, I will perform convolution and pooling operation for 4 stages. Finally, in the last pooling stage, I have considered 28 into 28 into 64. I have multiplied it and I have generated 50,176 neurons. Among 50,176 neurons, I have considered 64 neurons. Among 64 neurons, I have considered single neuron in the output layer to produce the output. Now I have shown the calculation for the number of parameters in the convolutional layer. In the first convolutional layer, I have taken 5x5 kernel, that is 25, and 8 is the number of kernel, 3 is the image size, 512 into 512 into 3. It is a 3-dimensional image, 3-channel image, plus 8. 25 into 8 into 3, plus 8 will give you the number of parameters. In the next convolutional layer, I have taken 16 kernels and 8 kernels in the previous convolutional layer. 16 into 8, 5x5 is the size of the kernel, plus 16 is the number of bias values. So after training this convolutional neural network on the face-only image dataset, I have generated the loss and accuracy plots. You can see the training loss and validation loss is decreasing, and the margin between training accuracy and validation accuracy is less. So the neural network is correctly converging and it is fitting well. Next, I have calculated the confusion matrix on the face-only image dataset, where 18 images are predicted as true negative, 2 images as true positive, 1 image as false negative, 0 image as false positive. I have calculated the evaluation matrix for the set 1 and set 2. 1 represents the set 1, not 1 represents set 2. I have calculated precision, recall, and F1 score by using the equations true positive plus true negative divided by true positive plus true negative plus false negative for accuracy. For precision, true positive divided by true positive plus false positive. For recall, true positive divided by true positive plus false negative. Next, I have calculated the macro average by taking the average of precision and recall for both set 1 and set 2 classes. F1 score is calculated by taking the harmonic mean of precision and recall. Next, I have generated receiver operating characteristic and precision recall characteristic to indicate the performance of the binary classification task, where you can see the area under curve value is 100%, which means it is having very good performance on the true class or the set 1 compared to set 2. So in this manner, I can conclude that I can use deep learning neural networks to perform three-dimensional object classification to obtain the results. These are the references. And if you have any questions, you can